All right, welcome back to the deep dive. Today, we're diving into a pretty fascinating paper. It's all about text-to-image generation. These models, they've gotten incredibly good. But removing unwanted content from them, it's kind of a mess, frankly. It's like, trying to perform surgery with a chainsaw.
Yeah, I see what you mean. A lot of power, but not a lot of finesse.
Exactly. And that's what makes this paper we're looking at today so interesting. It's called a Interpret-Then-Deactivate, or ITD. It uses this sparse autoencoder framework for concept erasure, and, well, it seems way more precise and scalable than what we've seen before.
Definitely a promising direction. I mean, the potential of text-to-image generation is huge, but there are some real concerns about misuse. Harmful content, explicit imagery, you name it.
Oh, absolutely. It's a big problem.
Right.
And right now, the ways we try to deal with it, they either kind of wreck the model's ability to generate, good images in general, or they're crazy expensive to implement.
You're hitting the nail on the head there. Fine-tuning the whole model. It can backfire. And adding specific modules, it gets really complex really fast.
So this ITD thing, it kind of goes about things differently. If I understand it right, it tries to figure out how the model's text encoder actually represents different concepts in the first place.
Exactly. And the way they do that is with this sparse autoencoder unsupervised model.
Right. Now, for those listening who are familiar with autoencoders, the key word here is sparse. Why is that so important in this context?
Well, it all comes down to interpretability. You know how deep learning models can be, total black boxes. But when you enforce sparsity, you force the autoencoder to learn a limited set of features. These features are the building blocks of meaning.
So instead of a jumbled mess of everything, it's more like essential ingredients.
Precisely. And the idea is that each concept, like let's say a particular celebrity or some unwanted content, it's represented by a unique combination of these sparse features.
Ah, so some features might be shared between concepts. Like, features related to the human body could be part of both person and explicit content.
Exactly. And that overlap, that's where other methods for erasing concepts kind of trip up.
They end up, like, throwing the baby out with the bathwater, right? Trying to get rid of the nudity. And they accidentally nuke the model's ability to generate any image of a person at all.
Yeah, that's a common problem.
Yeah.
So ITD aims to be much more targeted. It pinpoints the exact set of features strongly associated with a particular concept.
Mm-hmm.
And that's where their contrastive method comes in.
Okay, so walk me through that. How do they actually figure out what's unique about a concept's features?
Right. So let's say you want to prevent the generation of images related to, violence. They would look at the top activated sparse features for the tokens in violence. But then, and this is clever, they compare those to features activated by a set of normal concepts, things we don't want to erase.
So like a control group, almost.
In a way, yeah. By contrasting these two sets, they isolate the features that are unique to violence. Those are the ones they target for deactivation.
Got it. So then when someone types in a prompt with violence, only those specific features get deactivated.
Exactly. The model can still generate images of people, objects, scenes, just nothing related to violence because those unique features are essentially turned off.
That's pretty neat. And the paper mentions they can do this for multiple concepts at the same time, too.
Yep. No need to retrain the model or create new modules for each concept. That's a big deal for scalability.
Now, there's this zero-shot aspect of their concept classifier that I found intriguing. What's going on there?
So it's based on how well the sparse autoencoder can reconstruct an embedding. Basically, if the embedding contains a concept that has had features deactivated, the reconstruction will be worse, higher loss.
Ah, because it's missing some of the key ingredients, right?
Right. And they found that there's a clear difference in reconstruction loss between embeddings with targeted concepts and those without. So they set a threshold. If the loss is above it, boom, zero-shot classification.
That's a clever way to tell if a prompt needs to have features deactivated without explicitly training a separate classifier.
Exactly. Saves time and resources.
So to recap the whole ITD process, you train a sparse autoencoder on a bunch of text embeddings. It learns these basic sparse features. Then for each concept you want to block, you figure out its unique features by comparing it to safe concepts. And when generating an image, you use this reconstruction loss trick to see if you need to deactivate anything.
Spot on. And, the authors highlight three main contributions here. The ITD framework itself, using sparse autoencoders in this way for text-to-image models, which is, as far as they know, brand new, and their experimental results. And those results, they're pretty impressive.
Let's dig into those a bit. But first, I think it's worth spending a little more time on the sparse autoencoder itself. For those who might not be super familiar with the nuts and bolts, could you give us a quick breakdown?
Sure. At its core, an autoencoder learns a compressed representation of its input and then tries to rebuild the original from that compressed version. A sparse autoencoder adds a constraint. It forces the compressed version to have most of its neurons inactive.
So it's like finding the most essential information, right? Like the bare minimum needed to rebuild the original.
Exactly. Now, to get a bit technical, given an input vector, let's call it X, the encoder uses a weight matrix, a bias, and a ReLU activation function to map it to a hidden representation. We can call that Z. The ReLU is important because it introduces nonlinearity, meaning it sets negative values to 0. And the decoder then uses another weight matrix to try and reconstruct the original input from Z.
Okay, I'm following so far. So how does the sparsity actually get enforced during training?
Well, during training, the goal is to minimize the difference between the original input and the reconstructed one. But a sparse autoencoder also has an extra term in its loss function. It's there to promote sparsity in the hidden representation. Basically, it forces the network to use only a small subset of features to represent each input. And that's how it learns to break down complex concepts into these interpretable sparse features.
That makes a lot of sense. It's like forcing the network to speak in a more concise language, where each word carries a lot of meaning.
A great analogy. And then when applied to text embeddings, these sparse features end up capturing the fundamental meanings in the language.
So let's take a step back. Before we dive into the experiments, why is this whole concept erasure thing such a big deal in text-to-image models right now?
Look, the progress in these models has been amazing, but there's a dark side. They can be used to generate all sorts of harmful content. You've got misinformation, non-consensual imagery, harmful stereotypes. It's a minefield.
Yeah, it's not hard to imagine how things could go wrong. So concept erasure becomes this essential tool to make sure these models are used responsibly.
Exactly. And as we've touched on, the existing approaches have real limitations. Fine-tuning the whole model can mess up the good stuff. You try to remove nudity, and you might accidentally break the model's ability to generate images of people altogether.
Catastrophic forgetting, right? Kind of ironic.
Right. And fine-tuning can also introduce new biases, and its performance on stuff it hasn't seen before can be totally unpredictable.
So, not ideal. What about those methods where they add custom modules?
Well, they often don't generalize well. A module trained to suppress one thing might screw up the generation of something completely unrelated.
It's like a game of whack-a-mole. You fix one problem and another pops up somewhere else.
And of course, you'd need a new module for every concept you want to block, which quickly becomes impractical.
So, ITD's approach of working directly with the text embedding, before you even get to the heavy-duty image generation, it's much more strategic. But I'm still a little fuzzy on how they pick which features to deactivate.
It's not as simple as just turning off every feature that lights up for a given concept. That would be way too broad.
Right, because of those shared features we talked about.
Exactly. So they use this contrastive method. Let's say we want to block hate speech. First, they look at the top activated features across all the words in hate speech. But then they compare those to features activated by things we want to keep, things that are harmless.
So it's like subtraction in a way.
You could think of it that way. By subtracting the shared features, they're left with the ones unique to hate speech. And those are the ones they target for deactivation.
Makes sense. And if you want to block multiple concepts, you just combine the unique feature sets for each, right?
Precisely. No retraining needed, which is pretty elegant. So once they figured out which features to deactivate, how does that actually happen during image generation?
Yeah, walk us through that.
All right, so someone types in a prompt, and the text encoder turns it into an embedding. This embedding goes through their deactivation block.
Okay, and what happens inside the block?
First, the embedding is encoded into that sparse feature space using the pre-trained autoencoder. Then, they look at the activation of each feature in the erase set.
Which is that combined set of unique features for all the concepts you want to block.
Exactly. And for each feature in that set, they basically scale down its activation. They found that using a negative value for this scaling factor really effectively reduces the influence of unwanted features.
And the features that aren't in the erase set.
They're left alone. No changes. Finally, they decode this modified feature representation back into the embedding space. What you end up with is a modified embedding where the information related to the blocked concepts is basically gone.
So that modified embedding is what guides the image generation process. And the result is an image that hopefully doesn't contain the unwanted stuff. But didn't they also mention this zero-shot classifier? Like, they don't always do this deactivation.
Oh, right. You see, even though they try to pick features very specific to the unwanted concepts, there's always a chance that deactivating them could mess with other stuff. It's a complex system.
These models are like intricate webs, right? You tug on one thread and who knows what'll happen.
Yeah, that's a good way to put it. So, to minimize the risk, they use this zero-shot classifier. It's based on that reconstruction loss we talked about earlier. They basically try to reconstruct the original embedding. If the reconstruction is good, it means the embedding probably doesn't contain anything that needs to be blocked, so they leave it alone.
And if the reconstruction is bad,
then they use the deactivated version. It's like a safety check to make sure they're only making changes when necessary.
smart. It's like better safe than sorry.
Exactly. Now, the paper has this great visualization. They show how the reconstruction loss is clearly different for embeddings containing those targeted concepts compared to everything else.
Ah, so they can reliably tell them apart.
Right. That distinct separation is what makes the zero-shot classification work so well. It means the deactivation is only triggered when it needs to be.
All right, so let's finally get to those experimental results. They tested this on a few different things, right? Celebrity erasure, artistic styles, even explicit content. How did it perform?
It performed really well across the board. It was effective at removing the targeted stuff, and importantly, it did a much better job than other methods at keeping the good stuff intact.
So walk me through some of the specifics. Let's start with celebrity.
All right. So they were able to remove 50 different celebrities, and they tested to make sure that it didn't mess up the generation of 100 other celebrities, 100 different artistic styles, and these big data sets of image captions called Cocio and DiffusionDB.
Wow, that's a lot of testing.
Yeah, they were thorough. And consistently, ITD came out on top. They used metrics like CLIP score, which measures how well the generated image matches the text, and GCD accuracy, which looks at image diversity and quality.
And even on the DiffusionDB dataset, which I understand has all kinds of random user-generated prompts, ITD held up well.
It did. The image quality was almost as good as the original model, which suggests that those sparse features are generalizing pretty well.
So it wasn't just a fluke with celebrities. What about artistic styles?
They tested 100 different styles. And again, ITD effectively removed specific styles while preserving others. One interesting thing was that one of the baseline methods, reseller, really struggled with style erasure, which shows that different types of concepts can be tricky in different ways.
That makes sense. And what about the more sensitive stuff, the explicit content?
Well, they use keywords like nudity and sexual, and IED did the best job at reducing the amount of explicit content detected in the generated images. And this is all while maintaining good quality on the general Cocio dataset, which, again, that balance is key. You want to block the bad stuff, but you don't want to break the model's ability to generate normal stuff.
Absolutely. Did they do anything to test how robust ITD is? Like, what happens if someone tries to trick it?
Yes. They tested it against something called the unlearned diff attack. It's basically a way to craft prompts that are designed to sneak past content filters.
Kind of like an adversarial attack.
Exactly. And ITD did really well. It was much more resistant to these attacks than other methods, which suggests that messing with the underlying meaning in the text embedding makes it harder to fool the model.
So it's not just a surface level fix, it's getting to the heart of the problem.
Exactly. Now, they also did these ablation studies. They basically tweaked different parts of the system to see how much each piece mattered.
Always a good way to understand what's really driving the performance. So what did they find?
A few interesting things. First, that scaling factor they use to deactivate features. The strength of that deactivation is really important. If it's too weak, you don't fully block the concept. But if it's too strong, you risk messing up other things. And they found that different types of concepts might need different optimal strengths.
Ah, so a one-size-fits-all approach doesn't quite work.
Right. Then they looked at which layer of the text encoder was best for applying the sparse autoencoder. And while the classification accuracy for the remaining concepts was pretty consistent across layers, they found that the middle layers seemed to strike the best balance between erasing the target and keeping the overall scene structure intact.
So there's a sweet spot, it sounds like.
Yes, exactly. And finally, they looked at the size of the hidden layer in the sparse autoencoder, and they found that bigger is better, at least in this case. A larger hidden size lets the autoencoder learn more fine-grained features, which makes it better at distinguishing between different concepts.
So the more nuanced the model's understanding, the more precise its control. It's like giving it a finer set of tools to work with.
That's a good way to put it.
Yep.
So big picture, What do you think are the big takeaways from ITD?
Well, to me, it feels like a real step towards making these powerful models safer and more ethical to use. The idea of being able to precisely remove unwanted concepts without sacrificing the model's creative potential, it's huge.
I agree. It has implications for content moderation, for safety in AI systems, for giving users more control over what they see and create. And, the interpret-then-deactivate approach. It's a blueprint that could be used for other things, like controlling other aspects of generated content.
It definitely raises some interesting questions about how we'll interact with AI in the future. It's exciting, but it's also a little bit daunting.
For sure. This level of control opens up so many possibilities. But it also underscores the importance of thinking carefully about the ethics of it all.
Absolutely. We need to make sure we're using these tools responsibly. Well, for those listening who want to dig into the nitty-gritty, you can find a link to the paper in the show notes. And now it's time for our novel notions segment. We like to brainstorm a bit, think about where this research could lead.
I like that. So given how ITD works, using those sparse features and its zero-shot classification, one thing that popped into my head is, what if we could use it to proactively defend against new forms of harmful content?
Oh, interesting. Like as soon as some new horrible meme or dangerous idea starts spreading online.
Exactly. Imagine a system that's constantly monitoring trends, picking up on those new harmful concepts. And then, using maybe few-shot learning or meta-learning, it could rapidly figure out the sparse features for those new concepts.
So like an early warning system for AI.
In a way, yeah. And then it could automatically add those features to a block list for all the deployed text-to-image models. It'd be like a constantly evolving firewall against harmful content without needing to retrain those big models all the time.
That's a pretty wild idea. Do you think it's actually doable?
Well, IT's ability to handle multiple concepts and classify them in a zero-shot way, that's a good starting point. The real challenge would be figuring out how to automatically identify the sparse features for truly brand new concepts. But I don't think it's impossible, especially with all the progress in few-shot learning lately. I'd say it's a moderate probability in the, say, medium term.
So not science fiction, but not happening tomorrow.
Right. Now, here's another thought. ITD allows for very fine-grained control, right? So what if we could use that to build personalized content filters at the feature level?
So instead of just blocking broad categories like violence, a user could choose specific features they want to block.
Exactly. Someone might be okay with, say, stylized violence in a fantasy setting, but they want to block realistic depictions of injury. And they could customize their filter to reflect that.
That would give people a lot more agency over what they see online.
Yeah, and it fits with this trend of personalized experiences. The tech is there, thanks to the way ITD breaks down concepts into features. The challenge is building a user interface that makes sense.
So the bottleneck is more on the UX side.
Yeah. How do you let people choose what they want to block without overwhelming them? That's a tough problem. So I'd say the probability of this happening soon is a bit lower, maybe low to moderate. It really depends on how quickly we can figure out the UX side of things.
Well, those are some seriously thought-provoking notions. It's amazing to think about the possibilities and the challenges of this kind of technology. And of course, a reminder that our novel notions are just speculation. Who knows what the future holds?
Exactly. It's all part of the fun.
Well, that wrapped up our deep dive into Interpret-Then-Deactivate. Thanks for joining us.
Until next time.